As a math professor, I always like to make sure that my math superpowers are nice and sharp. And I actually haven't taught first year calculus in a couple years now. So I want to find out, can I even do integrals any longer? All of the integrals that we're going to do today have a little bit of spice to them, but still ultimately, I believe, if I'm correct, will be able to be done by first year calculus methods and don't need any sort of more complex tools like contour integration in the complex plane or anything like that. So feel free to follow along, try the problems yourself, and see if you can get to the same answers that I do. I'm going to begin here with this one. This is the integral of arcsine squared of x. How do I even begin on a kind of tricky integral like this? Now, when I look at this, there's not a lot of mess to it. It's sort of this one thing, arcsine, then it happens to be squared. So a sort of simplifying substitution, a u sub doesn't automatically apply. There's not some obvious algebra I can do. There's not any obvious sort of trigonometric identities that I can apply. I just have this particular integral. And it somewhat, to my eye, let's see if it works, screams out that integration by parts is going to work. I'm going to say that the arcsine squared of x is going to be u, and then the dx is going to be a dv. And the formula that I'm going to try and use is that the integral of u dv is equal to u times v minus the integral of v du. That's the integration by parts formula. I specify the u, and thus I can figure out what my du is going to be. It's going to be 2 times arcsine of x. And then by chain rule, the derivative of the inside, the derivative of arcsine, and I do know what the derivative of arcsine of x is, 1 over square root of 1 minus x squared. You can imagine some restriction on the domain, but nevertheless we have this result. If dv is just going to be dx, then I can say it pretty easily, v is just going to be equal to x. Okay, so I'm going to put those things into my formula. So this tells me that it's going to be u times v, which is x times arcsine squared of x. And then I need to subtract off the integral of v du. So I'm going to subtract off the integral of, I'll put the 2 on the outside, and then it's going to have an x up here, and then finally arcsine of x, all divided by square root of 1 minus x squared and dx. Now with integration, you sometimes don't know whether you've made a lot of progress or you haven't made a lot of progress. I look at this new tricky integral and it's gotten sort of messier, but perhaps it's quite nice. And I think it is here, because if I look at the x and the 1 over square root of 1 minus x squared, that I could actually integrate. I can integrate it with the u substitution. So I'm going to call this part in a new integration by parts, not to confuse my old one, I'll call that one dv, and then the arcsine portion, that's going to be my new u. And let me try and write down, therefore, what du is. du is going to be 1 over square root of 1 minus x squared dx. This reminds me I forgot a dx in my earlier formula, I'll add that in. And then what about for v? To integrate this one, I'm going to treat 1 minus x squared as one lump. Normally we call it u substitution, maybe I'll call it w substitution since I'm already using u. But either way, it's the 1 minus x squared to the negative 1/2. And then the x that I'm going to need from the derivative of the inside, that thankfully appears up on the top. And so if I put all this together, then I'm going to have a 1 minus x squared to the power of 1/2. I need to multiply by a 2 because when you differentiate the power of 1/2, that would bring out on 1/2, so I need a 2 to multiply that. But then there's also a minus 2x from the inside, so the 2's cancel, and I actually just have a minus sign. Okay, so with that, I can now come all the way back down here, and let's see what happens. Well, the first doesn't change, x arcsine squared of x. I see I have one minus sign up there, I have a second minus sign down there. If I put both of those together, I therefore get a plus times 2 of u dv, so that's going to be arcsine of x multiplied by 1 minus x squared to the power of 1/2. And then finally, I'm going to have my minus 2, and I have to do the integral of v du. Well, what's the v du? There's another minus sign, so it'll become a plus now, square root of 1 minus x squared up on the top here. And then the du is going to be, well, look at this, square root of 1 minus x squared on the bottom, dx. That is wonderful because that just cancels. And so this whole thing here is just going to become x. So the final answer will just be all of this, but get rid of all of that nonsense, and I can just put in an x. And of course, always important, your final plus c. All right, so that's our first integral done. It actually really wasn't so bad. It was just integration by parts twice in the end. It was just recognizing you had to use integration by parts because I could take the derivative of arc sine, and that was sort of all that I had in my integrand. It just made it pretty reasonable. Now, I did that, I think, correctly, but I very well may have made a mistake. So what I want to show you is my favorite app for actually solving integrals, to show you what the answer is and even all the steps to get there. And that is the sponsor for today's video, which is Maple Calculator. This is an app that you can download on your phone or your tablet. You take a picture of your hand-drawn equations, or you can type it in, and Maple Calculator figures out that it is an integral. It tells you what the answer to that integral was. It does it, and more importantly, it shows you how to do it. If you click the step buttons, it's going to show you a step-by-step process to evaluate this integral and many other types of integrals and many other types of math problems. This is what it looks like on my iPad, and if I actually check out the solution, I think I've made an error. It says minus 2x. Oh, and I did. I put plus 2x down. I see I missed the final negative when I did my final integration by parts. Minus v du as it's supposed to be. But let's imagine I didn't know how to do it. The favorite part is you click the steps button, which says show me how. And it's actually going to tell me exactly all the different steps. And you can see it. There's a couple different integration by parts. You can expand what one of those integration by parts are, and it's going to tell you all the different steps so you can follow along. If you're on a browser as opposed to your phone or your tablet, you can actually go to Maple Learn. This is their browser-based solution. Very similar to Maple Calculator, but actually even more powerful. And it's going to tell you all the steps to be able to solve these as well. Now, to be clear, I still think that there's a lot of value in being able to do integration by hand, to have a lot of procedural fluency at it, and it's just a really fun puzzle. So even though there's these incredibly powerful tools to help you, any tool can't solve every type of integral, and in building up our skills will allow us to understand and interpret the results that computer systems like these are going to give us. So it's important to still be able to sharpen those knives and do your integration basics, even though we have things like Maple Calculator and Maple Learn. Regardless, the links are down in the description for both of those, so I definitely encourage you to check them out. Now, to the next integral. This integral is a bit of an interesting one. So when I first thought about it, I saw some tan squareds and I thought, okay, I'm gonna definitely do some trig identity here and everything's just gonna work out and be really easy. But none of them actually work out very nicely. They just allow you to convert it to other also seemingly challenging integrals. So I had to find some way to sort of clean it up. And that makes me think I should do some type of u substitution. There's a couple candidates. Maybe u is tan of x, or u is tan squared of x, or maybe 1 minus tan squared of x. But if you use something like tan squared, its derivative is going to be like 2 tan secant squared. It's getting messier and not simpler. So let me try u is equal to tangent of x, and let's just see what happens if I do this substitution. Okay, if I take du, this is going to be equal to secant squared of x dx. And this is nice because I do know how to relate secant and tangent. This is because one of the 3 Pythagorean identities is that tan squared plus 1 is secant squared. So this secant squared can really just be written as tan squared plus 1 dx, and that's convenient because I just said that tan of x was u, right? So this is the same thing as u squared plus 1 dx. Okay, so that is quite promising that when I can take the derivative, I can get back my substitution inside of it. So let's see if we can plug it in, and I don't know, maybe this is going to be kind of nice. I can take an integral, and what do I have? Well, I have a 1 over 1 minus u squared. That's the 1 minus tan squared. But then, when I take dx and say that that's equal to du divided by 1 plus u squared, I'm going to have that factor as well. So 1 over 1 plus u squared, all of that times du. So in some ways, I'm doing better, that I have these sort of multiplication of 2 things. That's nice. It's no longer got any trigonometry on it. It's just a question of how do I deal with this rational integrand. And for that, we have a different method that screams out to us, which is, are you ready? Partial fractions, of course. That is, when I look at this integrand, I don't immediately know what its integral is. However, if I do this method of partial fractions, I can convert it into 1 over linear terms or 1 over quadratic terms. Both of those I know how to integrate. So this is actually a quartic on the bottom. A u squared times a u squared is me. A 1 over u to the 4th is the highest power. But if I can separate that into partial fractions, then I should be golden. Specifically, the question is going to be, can I write this as sum a divided by 1 minus u and sum b divided by 1 plus u? That's taking this first thing, noting 1 minus u squared is like 1 minus u, 1 plus u, so then I'm separating it out. And then finally plus cu plus d divided out by 1 plus u squared. 1 plus u squared is an irreducible quadratic. I can't factor that one into a product of two linears. It's okay if you want to skip this partial fractions bit. Actually, it's okay if you want to type the partial fractions into Maple Learn or Maple Calculator and let them evaluate it for it. I'm going to do it pretty quickly here, so let's just take the time lapse. All right, so I came in here to my partial fractions and I plugged in u equal to -1, which makes lots of nice terms disappear there, and u equal to 1, which makes lots of nice terms disappear there. And I also did 0 and 2 as well, and I got that these 4 values for the a, the b, the c, and the d. Now I can plug all of these into my integral, and then I should be able to evaluate that pretty simply. One of the things that makes partial fractions so nice is that I just get these linear or quadratic terms in the denominators after I execute the algorithm. And that's really useful because I know how to integrate both of those. Like 1 over 1 minus u is just going to be, well, 1/4. And then it's a logarithm of 1 minus u. And likewise for the 1 over 4, the logarithm of 1 plus u. So those are really nice. And then 1 over 1 plus u squared, for these quadratic ones, they're often related. Sometimes you have to complete the square, but we don't even have to do that here. They're often related to arctan. So in this case, it's just going to be 1/2, and this is exactly, it's just arctangent of u directly plus c. Final step, you have to do this every time. Take those u's and put them back in terms of x's. The first two terms were easy, I just did u equal to tan x, but now I have arctangent of tangent of x, which just becomes x. So there's going to be x divided by 2 plus c. This is actually only true when you appropriately restrict the domain on x. No worries. So, all right, second method down here. Ultimately, partial fractions was the thing that did the trick, but it was all about getting the right u substitution at the beginning that converted it into just being a partial fractions problem. Now, this integral has a lot of weird square roots, and as you well know, square roots just really screw up a lot of integrals. So what can I do? Often when I have a square root, I try to make the inside of that be just a u substitution, like say u equal to x plus 1, but there's two different types of square roots appearing here. If you try to make one of them the u, then the other one sort of just stays being messy. I can't clean up both of them at the same time. I could divide out by either square root of x plus 1, or I could divide out by square root of x minus 1. Those are options, but an option that I like, I think, best, and I think every time I see a whole bunch of square roots, is just to find the radical conjugate. What this is let me just erase my dx for a moment. I'm going to come up here. I'm going to multiply by a very funky version of 1. And this is just sort of, I have a bit of pattern recognition. Integrals that have these kind of square roots, you often try this little algebraic trickery. So the funny version of 1 that I'm going to multiply is on the top, it is square root of x plus 1 minus square root of x plus 1. And on the bottom, it's the exact same thing. Square root of x plus 1 minus square root of x plus 1. All of that, and then I have my original dx now stuck to the right. So I haven't done anything because I'm just multiplying by 1, the same thing on the top and the bottom. But what's relevant here is that in the bottom, it's the exact same expression, but I alternated the sign. That gives us our conjugate here. And the reason I do this is it's going to make my denominator really simple when I multiply it out. Indeed, if I do this, okay, let's do the denominator first because that's going to be nice. Well, the first two terms are going to multiply out and just be, well, x plus 1. Then I have two cross terms that takes things that look different. One gets a plus, one gets a minus, they both cancel. And then I get this square root of x minus 1 terms that multiply together. They get a minus sign, and then it's going to be an x minus 1. And heck, that could all just be canceled out, and we could just replace this with just 2. The denominator here is just 2. See how nice that algebraic trick makes the denominator? It's not going to be quite so nice on the numerator, but that's going to be okay. Okay, so what happens here? So if I first look at those two terms, this is going to become an x plus 1. If I look at the final two terms, so this is going to be minus minus is plus again. So this is going to be a, so that's going to be plus an x minus 1 this time. So very similar, but slightly different. The plus 1 and the minus 1 cancel, and then we're left with just a 2x. And then we have the cross terms, but the cross terms don't cancel this way. So what we're going to have is a minus 2 times the square root of x minus 1 times the square root of x plus 1, all of that dx. Okay, so the hard part here is just over there. The denominator's nice, the left-hand side of the numerator, that's going to be nice, nothing to worry about here. What we have to deal with is this portion that's circled. Now, because it's multiplication of the two radicals opposed to added together, this actually is a little nicer than it was before. I mean, what I could do here was treat this as just square root of x minus 1, x plus 1, all underneath the radical. And then that cleans up a little bit. This is just the same thing as square root of x squared minus 1. Okay, that is something I think I know how to deal with. So, I don't know, I'm feeling a little bit happy. So let's just do the parts of the integral that we know are easy. I've got a 2x on the top, divides out by the 2, just become an x on the top. That's going to be integrate and just leave me with an x squared divided by 2. For the second term, I have a 2 on the top and the bottom. Those just cancel. I have a minus sign, so I'm going to be subtracting off the integral of square root of x squared minus 1 dx. That's going to be my answer if I can figure out that. Okay, now challenge time again. Square root of x squared minus 1. This one is a trig substitution. And my heuristic for this is just that anytime you have things that are involving little quadratic terms like x squared plus or minus 1 or 1 plus or minus x squared, those quadratic terms look a lot like the kind of Pythagorean formulas that we have for all the trig expressions. So if you introduce some trigonometry here, you can take advantage of that. And the specific one that we want a formula for is going to be x equal to, which one's going to work? Not tangent, secant of theta. The reason for this is that secant squared of theta minus 1 is tan squared. So playing around with a secant squared minus 1 is going to work really nicely. If it was plus 1, you'd have to choose something different. Okay, so let's continue. If that's x, then our dx, the derivative of secant, last time I checked was secant of theta, tangent of theta, d theta. And so if I plug this in, well, nothing happens to the x squared divided by 2, of course, but I do get an integral of, well, square root secant squared of theta minus 1 times secant of theta times tangent of theta d theta. All that right stuff just being my dx. I get to use my trig identity. The secant squared minus 1 is just tan squared. Square root of tan squared is just tan. And then that allows me to rewrite this x squared divided by 2 minus the integral of tangent squared, 1 from the first one, 1 from into the dx, times secant of theta d theta. Now, when I analyze tan squared secant, unfortunately, there's not a lot that jumps out at me, as in I can't set u equal to tangent or u equal to secant. Neither of those just sort of becomes trivial. So I'm actually going to convert it to sines and cosines, which sometimes is a little bit easier, and see what I can do if I do that. So namely, I'm going to rewrite this as x squared divided by 2 minus the integral. Tan is sine over cosine, so there's a sine squared on the top, sine squared of theta. Then on the bottom, there's a cos squared coming from the tan squared, another cosine from the secant, which is 1 over cos. So it's a cos cubed on the bottom, but I know that the Pythagorean identities work really well with even powers of sines and cosines. So I don't want cos cubed on the bottom. Instead, I'm going to come here and I'm going to put cos to the 4th of theta. I can't just do willy-nilly. I have to come and cancel that. So I'll put an extra cos on the top. That gives me the cos to the 4th on the bottom, d theta. And now I think this is going to work out a little bit nicer because I can do a little u sub here. If I set u equal to sine of theta, well, then I have the du sitting right there, which is nice and convenient. That's what that cosine is going to do. But in particular, in the denominator, I know that cos squared is like 1 minus sine squared. In this case, 1 minus u squared. Because even powers, I can do that twice. And so what this is going to give me is, well, the normal x squared divided by 2 minus the integral of u squared du. That's what happens on the top. But then on the bottom, the cos squared becomes 1 minus sine squared, aka 1 minus u squared. And then all of that is squared because it's cos to the 4th on the bottom. So 2 different copies of cos squared. And this is much nicer for us because this is a rational function, and we know how to deal with that. That is going to be partial fractions. So, okay, let's try to figure out what that's going to be. I want to take this integrand, and I want to write it as a divided by 1 minus u. I'll note that 1 minus u squared can be written as 1 minus u times 1 plus u, so I've got an a over 1 minus u. And then because it's repeated, it's all this squared, there's also a b over 1 minus u squared. This is how we deal with repeated linear terms when we're doing partial fractions. Then I have a c term divided by 1 plus u, and finally a d term, because it's repeated, 1 plus u squared. So I got an A, a B, and a C, and a D. I have to solve them. Again, I'm going to not put you all through it all like this. I have to do it, so let's hit the time lapse, and I'll get those values for A, B, C, and D. Or you can pause and try to figure them out yourselves, if you're so inclined. All right, so I've done a little bit of investigation here, and A and C, it actually works out very nicely. It's just going to be 1/4, and B and D is just going to be -1/4. So what that means is that I'm trying to find the answer to, I'll put this 1/4 all the way up front, of 1 over 1 minus u plus 1 over 1 plus u, and then 1 over 1 minus u squared and 1 over 1 plus u squared. That's what I'm trying to integrate. Oops, I forgot my minus sign, so let me put them in there, minus and minus. And the real beauty here is because they're all 1 over linear, 1 over quadratic, I can integrate all of those. That's why partial fractions is just so nice. Okay, so this gives me 1/4 of logarithm of 1 minus u plus logarithm of 1 plus u, and then plus 1 over 1 minus u. If I take this derivative, that would give me a -1 and then another -1. Oops, I got my minuses incorrect. It is supposed to be a minus sign there. And this is the one that's going to be a plus 1 over 1 plus u. All of that's going to have a plus c. Now I'm close to be done, but the problem is I've got it in terms of u, I want it back in terms of the original, I want it back in terms of x. So let's try to remember what it was that u was equal to. Okay, u was equal to sine of theta, but theta is not equal to x, so what was theta? So sine of theta is where I'm trying to go to. Here's what secant of theta is. And so the standard trick here is you draw a triangle and you say, okay, look, our definition is that secant, which is 1 divided by cosine, is going to be x. So say cosine of x would be like 1 over here and x divided by there. This will give cosine of theta is 1 over x, and thus secant of theta is just equal to x. So by Pythagoras, if I want to complete the other side of this, this is going to be x squared minus 1, and then that would work. So if u is equal to sine of theta is going to be the opposite over the hypotenuse, then all the way back down at the bottom here, I can use the substitution that u is equal to square root of x squared minus 1 divided out by x. I put this into every single one of these spots here, everywhere a u exists, and that is my final answer. Now, you can go check this if you so wish with Maple Calculator or Maple Learn, but I do want to caution the one little thing about any of these computer algebra systems is that sometimes when you integrate, they may use a different set of steps than we did. Because of so many trig identities, the result can look different than your result, which doesn't mean that you're wrong. And the real test for this is you can take your result and differentiate it. You can use the Maple Calculator or Maple Learn to do the differentiation to save you the time if you so wish. But if you can differentiate it and get back to your original answer, then you're correct. All right, I hope you've enjoyed this little review, I suppose, on integration, some fun integration problems. If you like this video, please do give it a like for the YouTube algorithm. If you have any questions or you find any mistakes I made in the video, leave them down in the comments below, and we'll do some more math in the next video.